exponential functions. Right after learning power functions, we'll encounter something that looks very similar but is actually quite different. So what exactly is an exponential function? By definition, it's a function like y equals alpha to the power of x, which is distinct from power functions. In exponential functions, the variable x is the exponent placed at the top position. This relates to how the function is named. The exponent refers to the number at the top. So when we're confused between power and exponential functions and can't tell them apart, just remember, exponential functions have the variable in the exponent position. So the top number is the exponent and the bottom number is called the base, right? Since it's at the bottom. So what does the graph look like when the base alpha is a specific constant? We often hear the phrase exponential growth. Why is it called that? Because its graph looks like this, an explosively increasing curve. And furthermore, all exponential functions intersect with the y-axis at the fixed point 0, 1. No matter what the base alpha is, as long as the exponent x equals 0 at that point, alpha to the power of 0 will always equal 1. However, do all exponential function graphs look like this? Let's divide alpha into several representative ranges for discussion. First, if alpha is less than 0, can we even draw its graph? If alpha equals -1, which is less than 0, let's take a random point, say x equals 1 2/3. The function value would be -1, circumflex 1 2/3. In our previous video on power functions, we learned that 1 2/3 means cube root of square, so this would be cube root of square of -1. That's clearly not a real number. And whenever alpha is less than 0, we'll find similar examples. So we can say the base alpha of an exponential function cannot be less than 0. Well, what about when alpha equals 0? If alpha equals 0, its graph is a straight line coinciding with the x-axis, except we must exclude the point where x equals 0 because 0 to the power of 0 is undefined. Can we use 0? Let's set that aside and continue. Can alpha equal 1? 1 to the power of x always equals 1. It's a straight line parallel to the x-axis, which seems fine. But whether alpha equals 0, let's consider the case where alpha equals 1, although it can be graphed. But within the definition of exponential functions, it's not acceptable. Why is that? Because both cases result in unchanging straight lines. They don't reflect the trend of exponential functions, so they're excluded from our consideration. Now the definition is clear. For an exponential function with base alpha, it must satisfy being greater than 0 and not equal to 1. So what ranges remain? Are there only intervals a and b left? Let's first look at the simpler interval, b. The case where alpha is greater than 1, when the base alpha is greater than 1. As the exponent x increases, won't the function value also get larger? For example, when alpha equals 2, as x increases 1, 2, 3, the function value also increases. This is the most classic exponential function, a graph showing explosive growth passing through point 0, 1, monotonically increasing, approaching infinity upward, bounded below by 0. Of course, as x decreases, it gets closer to the x-axis, but never intersects it. The x-axis isn't just its asymptote, it's the common asymptote for all exponential functions. So then, now let's look at when alpha is between 0 and 1. We can take a specific example to understand better. For instance, let's take alpha equal to 1/2. Then this 1/2 circumflex x. Isn't it equal to 2 circumflex x divided by 1 circumflex x? And 1 circumflex x is just 1. This whole expression, how should we transform it? In the previous chapter, we learned for a b, we can directly treat the negative as a fraction with 1 on top to complete it. Converting back is also convenient. Remove the fraction and restore the negative. That's right, remove the fraction and restore the negative. This function equals 2 circumflex. X, what should its graph look like? Think about it. We just learned that y equals 2 circumflex x looks like this. So 2 circumflex x. Isn't it just reflected across the y-axis? All properties are reversed, monotonically decreasing, no upper bound, no minimum value, but approaching 0 asymptotically. Now we understand the basic graph types. When base alpha is greater than 1, we have a monotonically increasing function. When base alpha is between 0 and 1, we have a monotonically decreasing function. For other ranges, alpha cannot be used. Now let's use specific problems to consolidate what we've learned. First question, given function fx equals 1 to the power of x, 1. This base number is less than 1, so as x increases, the overall value decreases, monotonically decreasing. Now we need to solve the inequality. fa2, 4, f, 3a. So looking at the graph, isn't it like this? The red function value is larger, so the red variable must be smaller. Solving this as a standard quadratic inequality, we can calculate the final solution interval. Second question, given function f(x) equals the square root of 4x star 2tx2, find the domain for this function to be defined. What's under the square root must be greater than or equal to 0. But how should we handle 4x and 2x? Think about it. Let's start from the definition. X means x4, which can be rewritten as 2x2. Note that this is equivalent to 2x, so aren't these two parts both 2x? Oh, 4x equals 2x multiplied by 2x, which equals 2x2. And notice that x and 2 can exchange positions without issue. Not only that, in this case, multiplying 2 and x directly is also correct. We can derive a general formula for expressions like am and m and n can exchange positions or be multiplied together. Interested students can prove this. The process is quite simple. Let's return to our original problem. 4x can be transformed into 22xc. Here, 2 and x can exchange positions. After transformation, we can let 2x equal sine t. Of course, 2x is always greater than 0, with its graph above the x-axis. So now the remaining problem is solving the inequality t2, t2, us 0, where t, 0. We can calculate that t minus 1 or t plus 2. Since t is greater than 0, we can only use the positive part, but we're not finished yet. Finally, we need to convert t back to 2x, the right side of the inequality. 2 equals 21. As x increases, 2mx also increases, so we can determine that x1 is the domain of the function. In the next video, we'll introduce logarithmic functions.